Okay, so we're just going to make a start, everyone, for those joining on Teams. So hopefully you can see the slides. You can let me know in the chat if there's any issues with the audio or with the slides, but I'll hand over to Jenny, and Zainab is going to introduce things as well.
So it's a big pleasure to welcome Professor Jenny McKinley in Berlin. Professor Jenny is Professor of Mathematical Geoscience in School of Natural and Built Environment in Queen's University. I knew Jenny maybe 5 years ago or more, and worked together, and actually very vastly supported me to move from the traditional geologist to more interdisciplinary geologist, working in machine learning and integrating various data, including, just a lot of work we did. Okay, so thank you, and now I'll leave it to Jenny.
So thank you, and it's lovely to be here in Stirling, and thank you to everybody that's here in the room, and thank you to everybody that's joining us online. As Zainab says, I'm based in Queen's University, and that was a nice shot of our main Lanyon building, but I have to do the little marketing spiel for our university, but this is our Geography Elmwood building, and we're part of the School of Natural and Built Environment that actually includes not just geography, archaeology and paleoecology, but also civil engineering, architecture and planning. So I suppose just a shout out to our geography degree, that's both BSc and BA, and the range of areas that we cover, including GIS, which is the area that I work in mostly in undergraduate. And then a major, I suppose, shout out to our new Masters in Climate Change. And I think we're very excited about this. So this will start in September 2023. And we have a range of interdisciplinary colleagues, but it's based in geography and archaeology and paleoecology in the school. And we have a range of different colleagues that are experts in climate change that will be teaching on this module. So we're really excited about that. I also want to sort of put my director of the Centre for GIS and Geomatics hat on, and say that, we're very sort of pleased to represent the centre, and myself and colleagues across the school and university work in a whole area, including GIS, but also just a whole range of different spatial data, spatial data analysis, and also in geomatics. And my colleagues include Chris Lloyd, that some people here will know, but also Conor Graham and Will McGarry and many, many others. So we're very keen and happy to collaborate. And then my sort of, I suppose, final hat that I'm wearing today is from representing the International Association of Mathematical Geoscientists. And again, we have colleagues here that are long-term members of our association. And our role, I suppose we see it, is promoting worldwide the advancement of mathematics, statistics, and informatics in the geosciences. So it's bringing together those mathematicians, statisticians, informatics with the geoscientists to try and solve real-world problems. We have a fantastic conference coming up in Trondheim in August, and there's probably, you may even be aware of some of our range of publications that the IMG either owns these journals or associates with Springer and Elsevier for these journals. Any students listening or postdocs listening, we do have a range of different awards and also travel grants, so please do look up the website of the IMG and look at those opportunities. And I'm here as the 2023 Distinguished Lecturer, and the role of the Distinguished Lecturer is really to, I suppose, increase the awareness of the IMG and to give a series of lectures, and maybe in places that not necessarily, the students would be aware of it or come to our conferences. So today, the sort of talk title that I want to talk about is the use of this geochemistry, and in particular I'm going to be talking about compositional data analysis, and in particular I'm going to be exploring the environmental factors on health, and in particular on chronic kidney disease. But this project is linked to a much broader ESRC funded project space, which is looking at, what are the environments for the physical and social activity, particularly in sort of healthy aging and cognitive health. And I think looking at some of the expertise of colleagues in this school, I thought it'd be quite interesting and useful to put it in that context. So in this particular project, which I'll come back to, we're looking at, what are the geospatial factors in terms of cognitive health outcomes. In Northern Ireland, we have a major issue in that our pensioners are going to outnumber children by 2028. And that's going to put an increasing sort of demand on the economic system as a lot of these, retirees come out of work. It's estimated that on average 18% in each of our sort of council areas are age 65 and over. It's going to be 1 in 3 children born today are going to reach 100 years. Now that sounds fantastic, but if you think of that, how is that? Are they going to be healthy aging, or is that going to put a demand on the, the health system? So that's really the context of why this project is so important. And I'm just trying to change the slide. So the project aims, just very briefly, of the SPACE project is thinking about, where we live. Are we more vulnerable depending on where we live in terms of our cognitive development or impairment? And it's becoming very clear that factors that account for the most likely to develop this cognitive ill health are due to the environment. And it's less about how we live, but actually about where we live. And that's really important. And yet that hasn't really been explored. There's a lot about deprivation in that sort of area, but not necessarily about the environmental links into this. And again, how's that going to impact and provide evidence for policies in this whole area of healthy aging and brain health? So, what's in our environment, whether it's in our soil or whether it potentially is on something that we actually may take into the body, but also what's in the broader environment in terms of air quality, air pollution, and then how we interact with that is going to be so important. In terms of the broader picture, the World Health Organization states that 23% of global deaths are linked to the environment, and that's probably increasing. And as people will be aware, we do have trace elements, natural trace elements occurring in the environment and in our soils from geology, and they fall into these categories of essential elements, probably essential, but also these potentially toxic elements. And some of those will be well known, such as lead, cadmium, mercury, arsenic, aluminium, lithium, and tin. But there may be others as well that's coming not from geogenic, but also from anthropogenic sources. So in this particular talk, I want to talk and focus on chronic kidney disease. And I'm going to talk about chronic kidney disease of unknown etiology, but actually much broader than that. So chronic kidney disease is basically a collective term for the progressive renal failure. And again, that's increasing because the population is getting older, of obesity and diabetes. But it's the chronic kidney disease of unknown causes or unknown etiology, or CKDU, which is the one that's primarily linked to the environment. And that's increasing and is a worldwide concern, so much so that the WHO has set up a special task force in this area. There are known nephrotoxins such as lead, cadmium, mercury, and arsenic, but the link between those and potentially other ones is not completely well established. There's still a lot of unknowns in that. And the reason why that's so important is that, obviously that feeds into the progression of chronic kidney disease and diabetes and hypertension as well. So it's all linked. So for this talk that I'm presenting, we're using the UK Renal Registry data for Northern Ireland. And they collect data on patients before they start any form of treatment. So before dialysis or before a kidney transplant or replacement therapy. In other words, their body, it's before their bodies, I suppose, start to take on or start to be affected by any dialysis treatment. Again, the numbers for Northern Ireland on an annual basis may be quite low. So we're looking at a collective period between 2006 and 2016. And our census track areas are called super output areas. The data were provided for us in these age brackets. So basically all above 16, 16 to 39, 40 to 64, and then the 65 plus group. And then also this unknown etiology group. So in other words, this is registered by GPs, by medical practitioners. So it's not just us deciding that there's unknown causes, but they've actually registered this. So in terms of the standardized incidence rates, basically an incident rate of exactly 1 is what would be expected for an area like Northern Ireland based on our average age-specific incident rate. So anything above 1 is higher than expected, anything below 1 is lower than expected. And I should say this part of the work has been published. So if we just map those across Northern Ireland, you can see that we have particularly, I suppose, a problem for the 16 to 39-year-old in that we have several super output areas that are well above what you would expect. And again, obviously, interesting is this map for unknown etiology. And again, it's spatially variable, so it's not all over, which is interesting. But we have some of these super output areas that are up to 8 times higher than would be expected. So we have a problem, but we also have a problem with something that the GPs can't find a contributing and a health factor that might lead to it. If we look at Belfast in particular, again, we see the same problem, same trends appearing. So the 16 to 39-year-olds and also this area of unknown etiology. And for the Belfast area alone, it's up to 12 times higher than would be expected. So those are sort of quite, sort of unexpected or frightening numbers. And I should say that one of our colleagues, my colleagues and a co-author in this work, Damien Fogarty, is a leading practitioner in Northern Ireland in renal disease, and he actually was the one that brought this to our attention. So again, it's not the researcher thinking this is interesting, it's a clinician saying we have a problem here. We need to investigate this further. So a couple of other data sets we used are the deprivation measures. So a whole range of deprivation measures that again are available for Northern Ireland, but across the different devolved nations. For Northern Ireland, a score of 1 is the least deprived because there's a whole set of different measures and they're added up. So the higher number is the least deprived. And again, you can see it sort of very spatially across Belfast. And then we also have a very high resolution soil geochemical data set shown for Belfast area here, but also for the whole of Northern Ireland. And we know that there are potentially toxic naturally occurring elements. And we know that some geology domains and lithologies are sort of more, have a dominance of some of these potentially toxic elements, such as we know the flood basalts, the Paleogene basalts in Northern Ireland are high in cobalt, vanadium, chromium and nickel. And we know that some of our Silurian rocks are actually high naturally in arsenic and molybdenum. And maybe Zainab, you'll keep me right. I should have my phone in front of me. I don't see a clock in the room, so keep me right so I can go at the right pace. In Belfast, like many other cities across the UK, we have a sort of a industrial legacy, and that's an industrial legacy of contamination as well. From Harland and Wolff, our shipbuilding period, from various industries across associated with that. And more recently then we have, the Belfast City Airport, the only city I think that has 2 airports, Belfast International, Belfast City, and this is, in the heart of the city. So we know that we have anthropogenic sources coming from this. And you can see sort of the development of Belfast over time. So we have all of these different data sets. We want to integrate them, the renal data, the soil geochemistry, the deprivation data. So how do we do that? Well, one issue I suppose that I would like to raise at this point is that some of these data are actually proportional or relative in nature. So I suppose what the best sort of way to describe that is, if we have a 3% or 3 parts per million, is that large or small? And you might automatically say, well, it's small. But, it might be small compared with 80% or 80 parts per million, but is it small compared with 0.3 or 0.03 parts per million? So, the image on the right-hand side has no units, but all of those are proportional. So if one of these areas changes, then all the other ones will. So if we're trying to compare between these, then that proportionality may give us an artifact or a bias in our result. So if we're doing any statistical analysis or regression or any other statistical technique after using these data, we need to be careful about using these proportional data. And that's because they are constrained or closed data. And so in other words, they're vying for position, and if one changes, the other one will also change. Now, there are some really nice compositional data analysis techniques called log ratio transformations that can deal with these. I'm not going to go into detail in all of these. There's a body of work over the last sort of 15 years that has been developing these. And I suppose the more palatable way to describe these is that you can sort of think of them as a bar of Toblerone, much more palatable, bring in chocolate. But they are basically constrained within this sort of closed space. And we need to open them using an appropriate technique. So for this analysis, then, we want to use some of these techniques to open the closed, especially the geochemical data set. But if you think of also sometimes the deprivation data set as percentages. So again, we need to be very careful about using those. And we're going to use these compositional data analysis techniques and then use some further statistical regression models after that. One of the techniques that we've explored in this approach is using what's called a compositional balance approach. And the first one I'm going to just sort of describe is this CellBal algorithm, which again was conducted in R. And this sort of a compositional balance approach, and this is only one of a balance approach technique. There are many out there. And basically, we're going to use this to transform the data and then use that to identify the components. We actually identify a balance between components, not necessarily between one or two. It may be between one and three or others. But then use those identified balances in our regression models. And within this technique, there's a cross-validation procedure that identifies the best balance, and that is the one that comes up most of the time. So there's a frequency, and we use the mean squared error to determine the number of components, the best number of components in those balances. And then we use that for the regression models. So in this little example that I'm shown, it's for the super output areas, for the age standardized incidence rates for chronic kidney disease of unknown etiology with the soil potential toxic elements that have been derived from sort of the literature on renal disease and also the deprivation measures. And that's all of the different deprivation measures. And that includes income, employment, health deprivation and disability, education, skills, training, access to services, and living environment. And you can see the frequency of some of these balances that come up and the proportion, again, of how much some of these elements come up. What is some of the results then coming from this first stage of the analysis? So using the CellBal and a regression, some of the findings are for the chronic kidney disease of all ages, so in other words, the full data set. The strongest correlations are coming out with the multiple deprivation indices of employment and income. And these are the ones that have been linked to the socioeconomic factors such as smoking. So that's an interesting finding in itself. For the area that has been basically delineated for this historical industrial development, so we did it with all of the increasing, so the area is literally just the industrial areas. And obviously, you can see the sample size decreases at this. But again, the strongest correlation was coming with this chronic kidney disease of unknown etiology with the balance, the compositional balance of copper and antimony. Now, it doesn't mean that they are proportional. It means that there is some relationship, that these balances, these elements are important. But remember, because we've done the compositional analysis on them at log ratio, all of the other elements are taken into account, but these are still defined. So we don't need to worry about that, adjusting that compositional or relative issue, but they're still coming out as significant. And interestingly, these elements we know are linked to some of those industrial sources of contaminants such as smelting and, I suppose, the development of silver, lead and tin. There's an interesting relationship that is found between chronic kidney disease of unknown etiology or unknown causes and arsenic and molybdenum in particular. Now, we do know that we have natural causes for these from the geogenic rocks of Silurian. But if you actually look at the spatial pattern of these, it's the network, the transport networks that actually might shed a little bit further light on this. And again, for previous work that's been done in the literature, you can find that air pollution, traffic and brake wear emissions have been cited as a source for these heavy metals, so anthropogenic sources. And also arsenic and molybdenum have also been connected to atmospheric pollution, in particular traffic pollution. And it's brake wear, it's the brake pads emissions, and unfortunately this affects electric cars as well as, you know, the traditional cars. And they are an important source of antimony and molybdenum. So there's not very much research that has been done into air pollution and kidney disease. It's much more likely to be lung cancer or these other respiratory illnesses. But kidney disease is linked. But we do know from the literature, the medical literature, that these particles, these ultrafine particles of some of these sort of contaminants, such as lead, molybdenum and antimony, can get into the body through the blood, and then they can get to these other organs, including the kidneys, but including the brain and liver as well. And it is the source of these modern pollutants. And if we look at the world production of molybdenum, it is just increasing, and that's for the car, that's for the transport market, it's for brake pads. And again, unfortunately, it's not excluding, electric cars might be better, but I think we still brake. We brake too much. So I suppose one of the findings is that, you know, the urban soils of geochemistry can be used as a proxy for these nephrotoxins, but, you know, just for nephrotoxins, for renal, but also for these other chronic diseases. So obviously air atmospheric pollution was cited there. So I want to explore that a little bit further. And there has been a connection in the literature with PM 2.5, but again, there's a lot more work that needs to be done in this. So if we bring in the air pollution data into our analysis, and again, using the same sort of approaches, then it'd be interesting to see what is, if there's any relationship shown between the different air pollutants. So again, we're going to do it for the Belfast area. We're going to use both the chronic kidney disease of all of the age groups and the unknown etiology, and as well as the deprivation data, the geochemistry data. We're also going to bring in the air pollution data this time as well. So the nephrotoxins that we're using are listed there, and we use a geometric mean for each of the SOAs. But we're also going to use the air pollution covariates of benzene, carbon monoxide, nitrogen oxide, sulfur dioxide, and then the particulate matter of PM10 and then the PM 2.5 as well. Using this balance approach, and in particular this cell balance approach, then you can start to see that some of these elements and also the air pollutants start appearing within the balances as being really quite important. And again, if we run these through regression, then we can see how statistically significant they are. So again, we can just see some of these air pollutants coming up, appearing 64% of the time, and with the chronic kidney disease of unknown etiology appearing again about 68% of the time, and some of these elements, the nephrotoxins, coming up as again appearing a significant amount. So looking overall at these results then, using the generalized linear regression with a log link, we find that for the chronic kidney disease of all, so basically all SIRs above 16, molybdenum, zinc are coming out as significant, and also the multiple deprivation domains of employment, income, and health. And interestingly, for the air pollutants with chronic kidney disease, again of all the age groups, it's sulfur dioxide, and that appears 96% of the time, and carbon monoxide appears 66% of the time. So that's for chronic kidney disease. But for the chronic kidney disease of unknown etiology, carbon monoxide appears every time, 100%. Carbon monoxide comes up, and PM 2.5 in 68% of the trials. So there's previous work has shown that this may be linked, but not the carbon monoxide. And again, this is not necessarily with renal disease, this is more with the respiratory diseases. So certainly it supports the argument of PM2 exposure, but also shows that carbon monoxide and sulfur dioxide are also really relevant when you're looking at chronic kidney disease. So I want to explore a couple of things if I have time. And again, Zinni, please keep me. Are you okay for time? We want to, first of all, I mean, again, I suppose we need further research, and this is what we're doing, to look at the impact of these atmospheric pollutants, chronic kidney disease and cognitive health. But in this all across Northern Ireland, one of the things you probably have picked up is this chronic kidney disease of unknown etiology was very, very spatially defined, if I suppose, and we sort of know that we have flood basalts over this area. We have paleogene basalts, which is really quite interesting. So we're using the all Northern Ireland, there's the paleogene basalts, to explore the use of stream water geochemistry, because we have that as well, with renal disease, but also to try and look at a number of these different balance approaches. So we're going to use the CellBal algorithm. We're going to use another balance approach, which is called the sequential binary partition, which basically breaks it up in a sequential nature. And then another, the isometric log ratio balanced approach. And what we want to explore is, does the ordering of our variables have any effect on our outputs? Because obviously we need to know that our sort of, if we're presenting these, and again, it's new learning, it's new research, is it robust? So we did it for the whole of Northern Ireland, using all of the different types of geology across Northern Ireland. And I suppose the results that we found at that was we found a statistically significant relationship between the chronic kidney disease of unknown etiology and again, aluminium and arsenic. Again, those are known nephrotoxins, so that's interesting. But we really want to break it down for those basalts, the paleogene basalts, and see the impact of that. And if we stratify by geology, and in this particular case, the basalt bedrock, then again, this aluminium and iron is identified for unknown etiology. And that's interesting because we know that the aluminium and iron in stream waters, it is, I suppose, influenced by the bedrock geology, the superficial deposits, peat and others, and the amount of dissolved organic carbon and pH. And that's really interesting in terms of the impact on renal disease, and may shed light on the spatial distribution of the data. But the other thing that I really wanted, I suppose, to highlight in this study was, what's the impact of ordering? What's the impact of using these different balance approaches, and what's the impact of ordering the data? So in the top two graphs, this is for the whole of the Northern Ireland, so unstratified. This is the sequential binary partition, and you can see how it's sequentially divided up in terms of the different types of elements in terms of balances. And then this is the, I suppose, more traditionally used, the ILR balance approach, where it is much more of a data-driven approach. So this is for the whole of Northern Ireland, and then reordering in terms of our a knowledge-driven approach. Again, in terms of the sequential binary approach, it breaks it up. There are subtle changes, but it breaks it up in sort of the same way, using the ILR balanced approach. And again, comparing this with the CellBal approach. So our conclusions from that, I suppose, overall, the bedrock geology, superficial deposits, and the anthropogenic sources are all important in terms of understanding how it impacts on our health, not just for chronic kidney disease, but potentially for those other chronic diseases that have an impact on our aging population and on our cognitive development. There is I suppose, a warning that the ordering of elements, particularly for the sequential binary partition, will have an impact. And it does impact the ILR balance approach, but it's more subtle. It is generally known that a knowledge-driven approach is better, but I suppose even within that, I think knowing the impact of ordering the variables is very important. And we actually did find that the cell-bal approach was the more robust way to do that. So I just, I suppose, want to thank our sponsors for that, the TELUS and the UK Renal Registry data for that. But I wanted to bring it back to this space project very sort of just towards the end. So what are the next steps? So how does this feed into this ESRC space project? Well, this is the logic model of the whole of the space project. So you can see that we're looking at urban design, social environment, again, the byproducts of the urban design. So again, this is where the environmental factors come in, air pollution, but noise, temperature. Lifestyle will obviously be important. One area of the work package is looking at accelerometers on some of our aging population and where they actually move to. So can we validate our results on the ground? And then those will be linked to the pathways. So in terms of our chronic illness, even psychological stress, brain health and mental health. And we're obviously, this is a broad network interdisciplinary project that's working and based in the Centre for Public Health in Queen's. We are able to use this NICLA, this longitudinal cohort of the population. It was launched in 2013, so we have quite a nice longitudinal sample for this. It's a random sample of over about 8,500 men and women aged 58 years and above. And they have been interviewed on a series over that time period. And we're able to look at their social, economic, their biological factors. So we have our, information on their biological factors as well as their responses to various different types of tests. I suppose we can bring in this NICLA cohort. And what we want to do is to link that to the spatial environmental data. And that's what we're doing at the minute, bringing all of the different environmental data in together to see what this cohort's exposed to as a representation of the whole of the population and their lifestyle and also their cognitive development, their cognitive health development or impairment. So our objectives in our work package are what are the impacts and the effects between the local environment and the health outcomes. And these are the different types, and there's a broad range, I'll show on the next slide, the different types of environmental data that we're looking at. So our air pollutants, but also the noise, light, the soil geochemistry comes into play. The blue-green spaces that I know their colleagues in the school works in, and a whole range of different urban factors and urban impacts. So what we want to see is, from a person's location and movement, so their daily sort of habits, again, knowing their socioeconomic effects and their lifestyle, what is the impact also of the environmental exposure on that? These are just a range of the different data sets that we're analysing and bringing in. And we're actually creating a geoportal at the moment with a placement from Northern Ireland Ordnance Survey with us to generate this geoportal so that it can be linked to the health data. And as I say, one work package is actually using a subset of the NICLA cohort who've agreed to have these accelerators on their wrists. And so we actually know their movement. So we can validate, what they are actually exposed to during their usual daily commute or daily walks. So the health outcomes, I suppose, from this analysis, we want to do a sort of a network analysis. So we're going to graph where people live, their biology, their social, their urban interaction, and how that affects their cognitive health. We want to look at the exposure analysis, the local environment, the pollutants, all of the different synergies between those to, again, see the impact on their cognitive health outcomes. And I suppose in terms of the health outcomes, then we want to review all of that to assess, well, what's the impact? What is the advice then for public health policy to try and promote, I suppose, cognitive health and healthy aging within our wider environment? Just a little introduction to the broad team, interdisciplinary team within SPACE. And that comes brings me to the end. I'm not quite sure how long I've talked for, but so I think I've covered a whole range of things from research that's fed into this broader picture, and that is obviously ongoing. So I'd be very keen to take any questions or comments. So thank you very much.
Yeah, so we've got a bit of time. So if anyone has any questions, obviously in the room, if anyone has any questions on Teams, please either put them in the chat or you can raise your hand and we'll come to you in a moment. But the privilege goes to those in the room if you have a question first. So yes.
Thank you for that. That was very informative. I wanted to ask, you mentioned how we went from open to closed data sets in order to start using regression models. Would you be able to elaborate more into this process? Because I'm an outsider, so I wouldn't understand how you would close data.
So yeah, so the closed data, so by closed data I mean something like geochemistry, but there's a lot of population data. Percentages are obviously the, I suppose the easiest, that if a percentage changes, it'll impact the others because they add up to 100%. But geochemistry data, whether it adds up to 100% or is in parts per million or milligrams per kilogram, it doesn't really matter. They're still relative. In other words, if I take a sample and I remove, say a large proportion might be quartz, if I remove that, then in my sample, then the other elements in proportion will change accordingly. So we need to be careful because if we run tests, regression tests, particularly in things like stepwise regression, people have they've put everything in, removed a variable, and then run the analysis again and got a different outcome. That if you get a different outcome just because you removed an element, there's an issue there because it shouldn't impact the results. Whether you have a full set or whether you're using a subcomposition, but it will if you don't do some sort of analysis or transformation on the data before you do that. Compositional data analysis is I suppose it has started from John Aitchison, sort of way back. The additive log ratio would be one of the ones that is most, I suppose, in the early work, especially on water geochemistry. Then one of the elements is sort of sacrificed as the balance for some of the other ones. That is obviously has its benefits, but also its negative aspects in that you're always sacrificing one of the elements. Sometimes it's the major one that would be used. So I suppose colleagues within, I suppose it began within the IMG, the Mathematical Association, Mathematical Geoscience Association, but has developed into a compositional data analysis group in itself, have been working over a number of years developing different types of balances. Vera Pawlowski-Glan would be one of the key workers and various others, one who, her partner as well. But there's lots of different people working in this space. The centered log ratio is basically putting all of the elements over the geometric mean. And that again is quite helpful, but what happens sometimes with the centered log ratio is that some of the smaller elements might actually have more dominance than you might want. So all of these different log ratio approaches have positives and negatives. The isometric log ratio, and the isometric log ratio is actually part of a family of log ratios, is probably one of the most robust, and yet is probably one of the most hardest to understand or interpret. So when you transform, sometimes people like to back transform, and it's more difficult to do that. So there are lots of different approaches, and I wouldn't necessarily say one is better than the other. I mean, my preference sometimes is to use the ILR, the isometric log ratio, but I think the centered log ratio and then using PCA or something like that is quite helpful in plotting and seeing the relationship between those. So there's a whole range of different log ratio transformations that can be used, and it is, I think, probably best to explore using them. They're all available now within R scripts, so it's quite straightforward now to actually try some of these out, and different people have different R scripts to do it, but it is about understanding, being able to interpret your data And that's why I suppose putting the CLR into a PCA, which everybody sort of principal component analysis, which everybody's more familiar with, is quite helpful then, because then you can start to see the associations that are coming out. Does that, so is that a bit clearer, or? I mean, and I would encourage you to look up CODA association online, and there are workshops and there are conferences, and they give quite a lot of online talks. But certainly there are courses that I would encourage you to go along to. But it is about exploring which one people become sort of more comfortable using, and understanding that there may be limitations and restrictions to the use of these, but at least you're taking into account this relative or proportionality of the data, so you are more confident in your sort of the outputs that it produces, especially if taking it on to do any regression or anything like that.
Is that doable only through R, or can it be through SPSS? Sorry, is that possible only through R, or could it be could we use SPSS or some other?
So what I would suggest, SPSS does not have at the moment any log ratios that are built in to the actual software. But what you could do is do a transformation in an R package and then take the data out and do it in some sort of other statistical package. You do need to be careful, because obviously the natural correlations are no longer, you know, you have to be, you can't just take an ILR transformed ILR data and then put it into a correlation matrix. There is a particular sort of some people use heat maps. There are particular ways that people have developed to do that. So you do have to be careful with that. But yeah, some of the statistical packages within, or some of the statistical scripts within SPSS may be appropriate once the data have been log transformed. But it's not, unfortunately, that's not. It's not. It's. I don't think there's any. There is a CODA package which is on sort of Excel setup, which again will be downloadable from the CODA site, and it relates very quickly. You can see the R scripts and take it into R, but R is probably the most flexible way to do it.
Any other questions? Thank you very much, Jenny, for the talk. I was just quite inspired with what the ambition, you've outlined at the end with collating more data, and it looks like, and especially this where it sits like between the exposure from natural, and then the technical pollution, but also the lifestyle. So with the respect to lifestyle, just struck me that nowadays the more and more lifestyle aggregated data are becoming available. So I appreciate you have this cohort of targetedly sampled, but if you take a simple fitness, it aggregates the data. Okay, they're not labeled, but it gives you the general, like in which relative where people like tend to do more fitness outside. I wonder if this, maybe, I don't know how easy to get access to, but obviously these fitness companies, they collate a lot of data, probably with some level of analytics, you can get the density of here people mostly jog around, like, I don't know, sometimes more in that area. So do you think
so yeah, I mean, absolutely. I think our Fitbits now, and I think probably more of the 50s plus are using Fitbits than maybe did in the past. I suppose for the NICLA cohort, because we have been working with this cohort right through and using this same approach right through, we do have ownership through their permission. We do have ownership of the data we collect. It is consistent right across the cohort, and we have, I suppose, health indicators of these sort of participants as well. It seems like a very good idea to ask these companies for their downloads of data, but you probably know from even using Google or anything else, or these phone companies, it is not as open, and they still own the data. And even things like Google Maps, even the restrictions of what you have to go to get the data, you can't actually do any analysis. They still own it. You have to upload it. So these accelerometers we are able to download the data. We have developed a sort of a routine and a package to bring that data in, and then we have complete control over it. And we can also put into it the measures that we want to, specifically for cognitive health. So it's not just, you know, the Fitbit, what they might do, but it's actually, we want to test a whole range of different measures for this cohort that are bespoke to what we're looking at in cognitive health.
Yeah, I appreciate the cohort is, you have very high quality data there, but want to make inferences for a larger cohort.
Oh yeah, absolutely.
This
Yeah,
is
yeah.
where the rest of you calibrate to less labeled data.
Yeah.
Basically, what's the environment like?
Yeah.
People tend to.
Yeah. Yeah, but I think there's a commercial opportunity there, because, you know, you could have a bespoke Fitbit for the 50s plus or whatever, and it's actually geared towards and remind us of this, you know, what would actually be a healthy lifestyle for cognitive development, healthy cognitive development, and also the exposures that they might have come into contact through a certain, like a walk to pick up a paper, like a park, a walk in a park. Impact is, you know, there's a whole range of impacts, because you know, the air pollutants, but it's also what is the benefits of walking in a blue-green space or close to a blue-green space. And I suppose the news headline about in England, you know, that everybody should be within 15 minutes of a green or blue space is really important. But actually to measure what is the benefits of that. And if you're walking on a very, very busy road to get to that space, is there a pay, you know, what's the trade-off in that? And are you actually more exposed by trying to get there? Would you be better to jump on a bus, or are you safer in a car? You know, so it is a balance of lifestyle, activity, exposure, cognitive health, I think, that we are trying to explore. But yeah, I think there is a commercial, you know, potential for this.
Yeah, kind of following on from that, I suppose, Jenny. Do you look at the quality of the green and blue spaces, or the types of green and blue spaces, or do you just class them as green and blue? You're drilling down into it in a bit more detail.
So that's an interesting question. So at the moment, I suppose get access, and I should say there's another project that is running at the same time at this, which is called Groundswell, that is particularly looking at blue and green space. So it's like an offset, you know, another funded project is running alongside this. And in that particular project, they are mapping all of the blue and green space using the available data. That might be remote sensing, that might be information from, you know, where you have parks, public parks, and different types of blue and green space. And we're creating buffers around those, and proximity to our Nicola cohort. In Northern Ireland, there is a project that Outdoor NI are spearheading and working with lots of different organisations, including your National Trust and all of the different agencies, to try and integrate all of that blue and green space right across Northern Ireland. And that will bring in, that's really the goal, to bring in, because then it's information. It's actually, where is the access to that? Because you can have an area of green space, but if the only access is, you know, much further away than 15 minutes walking, it might look on a map that you've access to it, but you actually don't, because you're, you know, it's right round the other side, which is 2 kilometers away or something. So it's bringing in all of that, but we're still waiting on the data, that data set. And I think it varies, you know, whether in England and Scotland, what access, what is the availability of that integration, because there's lots of agencies involved who own, you know, the spatial data, if you like, and information on that. And again, it's, you know, coastal areas. And so, yes, I think you're absolutely right. There's more to it than just mapping an NDVI, you know, map output of green space. And a lot of it may not be publicly available. So, you know, that needs to be integrated into the whole equation as well.
Other questions? I have one. So particularly looking at the Belfast study with the kidney disease kind of element of it, I was interested. So although there was an element of the socioeconomic pattern based on the sort of IND kind of measures that you thought, I did wonder about the element of workplace and where particularly that cohort worked and where they lived, and the kind of the difficulty in distinguishing. Obviously, that's where people live in the pattern, but where the workplaces were and how that related to, you know, refineries and different things that were there before, shipbuilding, etc. And how is it the fact that they worked in these places, or is it the fact that they live in these places that are close potentially to those X sites of pollution, etc.
Yeah.
I don't know, can that be teased apart a bit with the data?
And it goes back to, I suppose, the questions, and obviously you can link it through a little bit to census data as well. But in this particular cohort, it does go back to the questions. Now, there's a whole range, there's a vast number of questions in the original questionnaire and then in the second cohort in the questionnaire. And they do take into account, obviously, where people live, and we do have exact locations of where people live. And if they have worked in that period of time. And you know, some of these people in the cohort may have joined the cohort at 50, but other people have joined when they have been retired. So, you know, work is not an issue. But you're absolutely right. And it's teasing out the question. Sometimes the challenge for us in the environmental and the spatial data aspect is that we look at the questions and think, oh, that could have been worded slightly better, so that we actually have a little bit more locational information. And some of them have been worded so that they can actually do a bit more analysis on the cognitive health side rather than the spatial location. The space project is probably, I mean, we are part of an international cohort, and there are different cohorts of the equivalent to Nicola right across the UK and Republic of Ireland. But I think the space project is innovative in that it is bringing in that environmental aspect, whereas in the past it has been medically driven or public health driven. So that location information isn't always seen, it has been seen as important. So they might have information on where people, if the people worked or not, but not necessarily exactly where they worked. So yeah, I agree with you, and we are trying to tease that out with the accelerometers, you know, where people are actually moving to, and some people will still be working. So you'll have that route and how they get there, and we'll be able to now look at those environmental exposures on that route. But yeah, both are important, obviously.
Because I've been involved in some work where, not with adults, but with younger people, whereby it's not so much where you live, it's kind of the route that you almost take, for example.
Exactly.
Because it's particularly on main roads, going via bus routes as opposed to being driven there, or again, having to walk on these main routes as well, is particularly exposure. Sometimes you lose some of that when you know they're individual where they live and their deprivation. You kind of miss some of the pattern in terms of the direction of travel they go. You can be kind of hidden a little bit by the other situations in the environment. So yeah, time for maybe one more question.
Actually, just a comment probably. With all these reconstruction, putting new routes like more cycle-friendly routes, etc. Yes, sometimes even segregated if put along a busy road, while this alternative maybe to put a park. So obviously the exposure is, it's difficult to measure quantitatively.
So yeah, so I mean, again, another project, so my colleagues, Professor Ruth Hunter has been involved in, who's a lead Centre for Public Health, is connected to greenways. So one of our Conswater Greenway is one of our major greenways in Belfast, and the development of that and the interaction and again the response from participants using that. But to cycle along a greenway, which is we would hope a greenway with nature-based solutions and various things along it, as opposed to a cycle lane on a busy road, is going to be a completely different, and the exposure you're going to get. I mean, there are interesting stats that you may be more exposed if you're actually in a car than if you're on your bike. And yeah, especially, you probably, if you're running or if you're on your bike, you probably should wear some sort of mask, but you don't wear them in cars. The other thing from the brake pads is that, we have these 20's plenty. We have these 20, especially outside schools and things like that, which is excellent. And again, work from Centre for Public Health has really developed that in Northern Ireland and getting that implemented. But for people to brake suddenly as they come into those 20-mile-an-hour zones is actually releasing, in my view, releasing molybdenum and these other toxic elements. So it isn't just about having these zones, it's about how the transition into them. And you do not want people braking suddenly. And actually that is as toxic, if not more toxic, than as well as obviously speed, but the moderate driving. So yeah, the take-home message is try not to brake, suddenly.
Speed bumps, like
Yeah.
traffic calming areas, you have to
Yeah. Exactly, and the noise implications of that, and the braking, and all of these things. So it's just all related. I mean, it gets very complex, and obviously, we also need to reduce speed. But yeah, it's a very complex situation. But I hope this project will tease out and provide an evidence base for some of those, because at the moment they're anecdotal. We sort of think that makes sense, but to actually have I suppose an evidence base for policy is what we're trying to provide.
I think we'll leave it there. We're just almost coming for 2 o'clock, so it just leaves us to thank Jenny again for a really interesting talk.
Thank you.
Some applause on Teams as well for you.